Hello everyone. In this lecture, I want to talk about how to use R to perform the linear regression analysis. The linear regression model is one of the most frequently used models in business analytics. It can help us to investigate how one factor influences another factor. In this lecture, I want to use an example to show everyone how to perform linear regression analysis in R. Let's see the example. Joe is a mobile app developer. He has a fitness app that offers the health information to users. Joe wants to bring his business to the next level. He wants to know more about the user population. Here we meet a new concept, population. I will talk about this concept in greater detail later in this lecture. Joe's question is, how would a user's yearly incomes influence the user's weekly length of usage of the mobile app? Joe has more than 2 million users. It's impossible for him to survey the entire population. So what he did was he drew a sample of 100 users and asked them how much they make every year and how long they would use the mobile app every week. We meet another new concept, sample. We'll talk about it later in this lecture. We want to build a linear regression model to analyze how a user's yearly incomes can influence how long she would use the mobile app every week. Before I talk about the linear regression model, I want to introduce some terminologies to everyone. First, population. A population is a group of research interests. Corresponding to population, we have another concept called a sample. A sample is a part of a population. In our example, Joe's 2 million mobile app users is the population. That is the group we are interested in. Because we are unable to survey every one of the users in the 2 million population, we only look at 100 users. These 100 users formed a sample. It provides an opportunity for us to look at the sample, and then we want to infer the findings from the sample to the population. It's very important to differentiate these two concepts. Keep in mind that we are interested in the relationship between yearly incomes and how long the mobile app user will use the app of the population. We just use the sample as an example to look at the relationship, and then we want to find a way to infer the findings from the sample to the population. We'll further talk about this relationship later in this lecture. We have another two important concepts, dependent variable and independent variable. A dependent variable is a factor being influenced by others. An independent variable is a factor that influences others. In our case, we want to look at how the user's yearly incomes influence how long she would use the mobile app. Then how long she would use the mobile app is a dependent variable. The user's yearly incomes is then the independent variable. Keep in mind about these two concepts. Now let's talk about how to perform the linear regression analysis in R. We talked about data visualization in previous lectures. Before the analysis, let's take a look at the relationship between incomes and the user's usage hours in a graph. Let's have an intuitive visualization about the relationship. Let's go back to the PowerPoint. Let's use the ggplot2 package to draw the graph. You can copy the codes from the PowerPoint to the R software. Let's paste the code. Now you can see there is some kind of a trend between the two factors, right? The more the user's yearly incomes are, the longer he or she will be using the mobile app. This is how we show the relationship in a graph. Let's close this graph and then go back to the R software. To perform the linear analysis, we want to find out the exact mathematical relationship between hours and incomes. We want to see how the user's incomes influence how long she will be using the mobile app. This is what I want to do. First, I want to create a variable called simple reg. This variable will hold the analysis result. And then I want to type in the linear regression analysis function name, LM. Inside of the parentheses, we want to specify two parameters. First, the model we want to analyze. I want to type in hours, a tilde sign, and then incomes. Notice that hours is a dependent variable. It is on the left side of the tilde sign. Incomes is an independent variable. It is on the right side of the tilde sign. By doing this, the LM function can analyze how a user's incomes influence the user's usage hours. And then a comma. Next, I want to indicate what is the source data frame. We already read the data into fitness, so the source data frame is fitness. I want to type in data equals to fitness, and then press enter. Now I get the analysis result. If you want to take a look at the results, you can type in summary. Between parentheses, type in the variable that holds the result, simple reg, and then press enter. This is the analysis result. I already copied the screenshot into the PowerPoint. So let's go back to the PowerPoint and talk about how to analyze the result. When we get the analysis result, the first factor we want to look at is estimate. It is the coefficient of an independent variable. It shows how the independent variable can influence the dependent variable. According to the given numbers here, we can build an equation like the one listed on this slide. Hours equals to 1.464, which is the estimate for the intercept, plus 0.066 times the incomes factor. How can we use this equation? Suppose now we have a new customer. We don't know how long she will be using the mobile app. So we will ask her how much she can make every year. She told us she can make $100,000 a year. So we plug in 100 into the equation on this slide. And then we can predict how long she will be using the mobile app. The estimated hours is 8.06 hours, according to the equation we built from the analysis result. Next, we want to figure out a relationship. At the beginning of this lecture, I talked about the difference between population and sample. I said population is a group we are really interested in. We actually want to figure out how the user's incomes influence how long the user uses the mobile app among the population. But because population is so difficult, so costly to survey, to study, we really cannot look at the population. That's why we draw a sample from this population. Currently, we build the relationship between hours and incomes. From this sample, from the current sample, I see hours equals to 1.464 plus 0.066 times incomes. From this sample, I found how the user's incomes influences how long she will use the mobile app. But the question is, does this equation still hold in the entire population? How can you convince the data user? You build a model from 100 samples, and you can infer the model into the population. This is a very good question, right? In order to achieve this goal, we want to compare p-values to the level of significance. In practice, the level of significance is usually set at 0.05 or 0.01. These are the standards for us to infer the relationship from the sample to the population. It's up to the business analyst to choose which value to use. You can choose either 0.05 or 0.01. In medical research, you want to choose a smaller number, so you want to make the standard even more stricter. In business analytics, 0.05 is an acceptable level of significance. After you identify the level of significance value, the next value you want to look at is called a p-value. P-value is the value you get from the data analysis result. If p-value for an independent variable is less than the level of significance value, we call this independent variable a significant influential factor of the dependent variable. In other words, if an independent variable is significant, its coefficient can be inferred to the population. In R, p-value is showed as PR value. So when you get the result, when you want to check the p-value for each independent variable, look at the PR column. Here we have a p-value for incomes. This value is less than 2 times E negative 16. E negative 16 in R represents 10 with the power of negative 16. This number will generate a very small number, so small that it will be very close to 0. So the p-value for incomes is very, very close to 0. No matter you use 0.05 or 0.01 as the level of significance, this p-value is always smaller than the level of significance value. So what conclusion can we make? We can see that incomes is a significant influential factor to ours. In other words, we can infer the equation we built here to the population. In the future, you can randomly choose any customers from this 2 million population. Ask this customer how much he or she can make every year. And then you can use the incomes value to predict how long he or she will be using the mobile app. Some classmates may have a question. What if the p-value of an independent variable is greater than the level of significance value, no matter it's 0.01 or 0.05? What conclusion can I make for that case? Since the p-value is greater than the level of significance, we cannot see that independent variable is a significant influential factor to the dependent variable. In other words, the model we built from that sample cannot be applied to the population. What should we do then? We are interested in the population, but we cannot apply the model to the population. What should we do? We have to draw another sample to see if the p-value of the independent variable is significant in another sample. If not, we have to draw the third sample until we get the p-value is less than the level of significance. This is the knowledge we can get from the p-value. The third factor we want to look at in the analysis report is the r-squared value. The formal name for r-squared value is the coefficient of determination. It shows the percentage of the dependent variable's change that can be predicted by the independent variable. In the R report, we have a multiple r-squared value or the adjusted r-squared value. You can use either one of these two values. Let's use the adjusted r-squared value as an example. From this report, we can see that the adjusted r-squared value is 0.65. I round the number to 2 digits after the decimal points. As you can see here, 0.65. What does this mean? That means if a user's usage hour changes by 1 hour, either increases by 1 hour or decreases by 1 hour, no matter what, about 65% of this 1 hour change can be predicted by the independent variable, which is incomes in our case. The r-squared value shows the independent variable's predictive power on the dependent variable. This is the information that r-squared value tells us. Some classmates may have a question. In this case, I only predicted about 65% of the user's usage hour. What about the other 35%? How can I predict the other 35%? We can keep adding the independent variables into the model. For instance, besides incomes, in a new model, we want to use incomes and gym visit frequency, the two independent variables, to predict the usage hours. Let me show everyone how to add a new independent variable into the model. Let's go back to the R software. Now we want to build a new model. Let's create a variable called multiple reg. This variable will hold the result from the new analysis. We still use the LM function. Let's indicate the two parameters. In the first parameter, I want to type in hours and then a tilde sign. Next, I type in incomes. This is the model we built for the previous example. Now we want to add gym visit frequency as another independent variable. What we can do is to type in a plus sign and then type in gym visits and then a comma. By doing this, we tell the R software that we want to use incomes and gym visits as two independent variables to predict the usage hour. The second parameter is source data frame. We type in data equals to fitness. Press enter. Now we already get the result. If we want to take a look at the result, we type in summary and then multiple reg. This is the result. I already get the screen capture in the PowerPoint. So let's go back to the PowerPoint and then analyze it. The first factor we want to look at in the result is the estimate. By using the estimated coefficients, we can build the model on this slide. Next, we want to look at the p-value for each independent variable, as you can see here. The p-values are very small, so we can say both of them are significant influential factors to the dependent variable. This means the equation we built here can be applied to the population. In the future, we randomly choose any user from the 2 million population, ask them how much he or she can make every year, how many times he or she visits gyms every week. Plug in those two numbers, then we can predict how long he or she will be using the mobile app. The third parameter we want to look at is the adjusted R-squared value. Here the value changes to 0.79. It increases from 0.65 to 0.79. What does this mean? This means we get more predictive power by using the new equation. Why? Because we added a new independent variable, gym visits. We look at the hours change from more perspectives now. That's why our equation has more predictive power on the dependent variable hours. This is how we interpret the analysis result. In a linear regression model, if you only have one independent variable, that model is called a simple regression analysis. If you have two or more independent variables, that model is called a multiple regression analysis. In our data set, we also have a vector called state. What if we want to add it as the third independent variable into the multiple linear regression analysis? Let's take a look at the data set. We stored the original data set into the data frame called fitness. So let's take a look at fitness structure. Let's use head function and then type in fitness between parentheses. As you can see, besides incomes and gym visits, we had the third vector called state. Now we want to use these three vectors as three independent variables to study how they influence how long the user will be using the mobile app. The head function only shows a few data records at the beginning of the data set. We have 100 data records, right? So let's group the data records according to where the customers are from. Let's use the order function to rank the data and then take a look at how many states do we have in this data frame. Let's create a data frame variable called ranked. And then we want to rank the fitness data frame by state vector. Let's type in fitness and then the square brackets. Inside of the square brackets, we want to use the order function. And then in the inner parentheses, let's type in fitness, a $, and then state. Outside of the parentheses, we want to type in a comma. This means we want to rank the fitness data frame by the state vector. We want to group the customers according to their states of residence. Let's press enter. We get a ranked data frame. If we want to take a look at this data frame, let's type in ranked. Now you can see we have all 100 data records listed in our software. Let's see the states we have. We have California, CA, right? Next state, Maryland. Next state, North Dakota, ND. Next state, New York. Next state, SD, South Dakota. And then TX, Texas. Next, WA, Washington. So totally we have 7 states. This is the overview of this data frame. Now we want to build the linear model. Let's say we want to create a variable called multiple 2. This variable will hold the second multiple linear analysis results. Let's type in LM, and then between parentheses, the first parameter should be hours, and then a tilde sign, and then incomes plus gym visits plus state. Notice that all the variable names are as same as the vector names in the data frame. And then a comma. Data should be either fitness or ranked, doesn't matter. In ranked, we just grouped the customer. We really didn't change any data in ranked data. So you can use either fitness or ranked as the source data frame. Next, we want to press enter to get the result. And then we want to use summary to see the result. Between the parentheses, we want to type in multiple 2 so that we can show the result. Here is the result. I already copied the screen capture, so let's go back to the PowerPoint to take a look at the result. From the analysis result, the first factor we want to look at is the estimate, right? According to the given numbers, we can build an equation like the one on this slide, the hours equation. 0.79 plus 0.06 times incomes. 0.06 is the estimate for incomes factor, right? As you can see here. I round the number to the 2 positions after the decimal point. So I round 0.055 to 0.06. This is the coefficient for incomes factor. And then for gym visit, we have a 0.44. So we use 0.44 times gym visits in the equation. Next, for state Maryland, we do have customers from Maryland, state MD, right? The coefficient for this factor is negative 0.24. So I round the number in the equation. I should have a negative 0.25 times state MD. Same thing for customers from North Dakota, from New York, from South Dakota, Texas, and Washington. How can we use this model? Let's take a look at an example. Suppose a customer gives us the following answers. He said his yearly income is about $80,000. He visits gym about 5 times a week, and he's from Texas. Now we can plug in these numbers into the equation we just got. For instance, we replace incomes with 80. This is the customer's yearly income, right? We replace gym visits with 5. This is reported gym visit frequencies every week. But how can we show this customer is from Texas? For categorical data, like where this customer is from, gender, and so on, we want to use value 1 to indicate a customer belongs to a category. We want to use value 0 to indicate a customer does not belong to certain category. In our case, this customer is from Texas, so we give a value 1 to the state TX variable in our equation. For other state variables, we give value 0s. That's why we get the equation like the one listed at the bottom on this slide. For state TX, we give value 1. For other states like Maryland, North Dakota, New York, we give value 0s. Finally, we can predict that this customer will be using the mobile app for 8.2 hours every week. This is one application of the state independent variable. Another application is we can assume that incomes and gym visits are the same. And then we can compare users from which state will be using the mobile app longer or shorter. Let's see an example. Suppose we have a customer from Maryland. And then for this equation, we should give value 1 to the state MD variable, right? Because he's from Maryland. So we give 1 to state MD. Since he's from Maryland, then he's not from all other states. for state ND, state NY, state SD, state TX, state WA, we give zeros. Finally, we will build an equation like the one on this slide. At the end, notice that we will minus 0.25 hours. Then we can find another customer. This customer is from North Dakota, state ND. So for ND, we should give value 1. And then for all other state variables, we should give zeros. Finally, we'll get the equation on this slide. As you can see, at the end, we should plus 0.49. If the customer is from North Dakota, we should plus 0.49 at the end of this equation. If the customer is from Maryland, we should minus 0.25 at the end of the equation. What does this mean? This means if a customer from North Dakota and a customer from Maryland have the same yearly incomes and visit gyms at the same frequency, then the customer from North Dakota will be using the mobile app longer than the customer from Maryland. Using the same principle, we can build the equations for customers from other states. From this comparison, you can see that if the incomes and gym visits are the same, the customers from Washington will be using the mobile app the longest. Why? Because at the end of the equation for Washington customer, we need to plus 1.12. This is the largest addition to the equation. Which customer will be using the mobile app the shortest? We find out New York City. Why? Because for customers from New York, we need to minus 0.57. This is the largest subtraction from the equation. By doing this, we can rank the customers from different states according to the length of time they will be using in this mobile app. Notice that in the output, we don't have a state CA. Why is that? Because our software will randomly choose a base category. And then for this base category, we don't add or subtract anything. CA is chosen as a base category in this case. So at the end of the equation for customers from California, we didn't add or minus anything. This is the one point you should notice when you interpret the result for state variable. The state variable is different from incomes and gym visits, right? State just shows which category a customer belongs to. If you have a variable which has categories as values, we call this variable a dummy variable. In our case, we have a dummy variable called the state. And we have Texas, Maryland, North Dakota, and so on. Totally, we have 7 states. So the dummy variable state has 7 values. They are the 7 states we have in the dataset. By using the dummy variable, we can compare the performance between groups. For instance, users from which state will be using the mobile app longer or shorter. This is how we use dummy variable in the linear analysis.